is the second law. Cap first, second law. On the Kepler's second law, we are talking about is the radius of the vector drawn from the sun to any planet split our ego areas in the ego time interval. Now, so here is the sun, and here is the elliptical orbit. So, so if this is and here is this area, we like to say is A, and this area is considered as a B. So B. So for this, this is called radius here. It's sweeping this area, and this one sweeping from here to here. And if this area A is equal to B, then it says in equal time interval. That means when you come from here, delta TA is equal to, from here to here, is called delta TB. So we say the area A equal to area B, then delta TA is equal to delta TB. So from this, you can probably know that when it's sweeping from here to here, the orbital speed of the Earth are slower. In here, the orbital speed is faster. So that's what he developed, and he proved that in the equation. So number 3 that is turned out to be more useful is number 3. Number 3 is called Kepler's the third law. Kepler's third law. The Kepler's third law saying that in that cases is saying that the square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. So, so it says the square of the orbital period of any planet is proportional to the cube of the semi-axis. So we like to written it into a formula way. So this is the elliptical orbit, and this is a sun is in here, and the Earth is here. So what does it mean? That is, suppose the axis, this is one A, and this is a short one, semi-axis A and B. And what he's saying that T times A to the cube. So that's all that is on the Newton's, the Kepler's third law. And it can be proved that very easily. How to prove that is on the gravitation law. So of course, we can do it very easy with the circle. But if you want to do it for the ellipse, that takes more doing for math. For circle, it's very easy to do. Here is a circle. And so this is orbital speed. In these cases, you have two things is involved. This is a V, and then of course this is a V. And during this circular motion, two forces is important. One is they call F sub C. Another one is gravitational force. So F sub G is equal to F sub C. So if you're using this as a base, then you can develop the whole formula. F sub G, in which cases, if you like, the center of mass is ME, and here is M. Okay. In the book is the mass of the sun, and then here is mass of the planet. So that F sub G equals G, the mass of the sun, and the mass of planet divided by R squared. And then this one is M planet, MP. And that is V squared divided by R. So with this as your starting point, and then after you calculate V, then what is V? V is equal to 2 pi R divided by T. So if you're using all this information, then you will getting down to that equation. So step by step, then you got it. So the other one is we want to escape the control by the gravitational force. So how to getting out of it? So on the 11.4 section, we do these calculations. That means after the Cavendish doing the job, finding out the gravity constant, then we can do a lot of calculation. Export. I don't know, it says in 2 to 5 years, double the export. Where are we going to sell? Satellite. So maybe you lower the price or jack up the price. Any other people cannot make the satellite. So United States make the satellite, then jump up the price 2 times because they can't do it. So we United States can do it. The other one is building up your selling more weapon, right? So then we can do that. So how to put the satellite? So this one is the Earth, and then this one want to get out. So in these cases, we like to say it have an initial velocity, and then after that we want to go to the final velocity is equal to 0. So we go come to that. So this is the case. How to get it? So first of all, we like to say you can using energy conservation. Initially, that is kinetic energy and potential energy, and then after that, because V sub bar F equals 0, so that we have only potential energy. So conservation of energy. Conservation of energy. Okay, then you will have 1.5 m v sub I squared minus g. This is kinetic energy. G m e m divided by r e. RE is here. This one is M, and this one is ME. That is equal to what we call kinetic energy minus GMEM divided by R max. In which case, the R max is right at this point. This is R max. R max can be infinity, so this term is dropping out. So from this, you should be able to transfer. This is equal to 0. You should be able to, all this turn out to be 0, then you can find out the V sub escape velocity equal to square root of 2G ME divided by RE. After this is done, then the people, when they are doing the rocket, they will figure out how to get out of the control of the what we call the gravitation law. And the 11.4 is done, so that for your homework, even though we are not stressing on this chapter, so I will still like you to do the homework on 37, 35, and 17. Those are scheduled homework for you to hand it in. So please hand it in as soon as possible, and so that Hadrian can make the completion. Okay. So today we